Okay, here are a few more exercises involving circuits with DC sources. Let's try to determine the Thevenin equivalent of these three circuits as seen from terminals A and B. And then for part A, or for figure A, let's determine the value for which maximum power is dissipated. So let's solve part A first. So to solve part A, so what we really want to do is for each of these circuits to be converted into something like this. So RTH and VTH. Okay, and we can solve for VTH and RTH separately. To solve for VTH, we don't involve RL, so we remove RL from this figure and then solve VTH, which is just the voltage across A and B. And then to solve for RTH, we replace the source voltage with a short, or with a with a wire, okay, and obtain the equivalent resistance as seen across terminals A and B. Okay, so to solve for VTH, keeping A and B open, we see that this is a voltage divider equation. R4 doesn't have a voltage. And why is that? Because if these two are open, then there is no current going through R4. There's no current going from this junction towards R4. So all current is passing through R1, R2, and back to R3. Okay, so in this case, we use the voltage divider equation. So the Thevenin voltage is simply equal to R2 over R1 plus R2 plus R3 times 2.5 volts, okay, which is then equal to 78 ohms divided by 100 ohms plus 78 ohms plus 47 ohms times 2.5 volts. So the Thevenin voltage in this circuit is then 0.87 volts. Okay, what about the Thevenin resistance? So to solve for the Thevenin resistance, we replace this DC source with a short. So that's just a wire, which means that 47 ohm resistor and the 100 ohm resistor are in series, and the equivalent series resistance is parallel to R2. Okay, so that means that the resistance as seen through AB is just a series parallel equivalent of R1, R2, and R3. So we can solve for RTH to be 1 over R2 plus 1 over R1 plus R3. Okay, plugging in the values, we have 1 over 78 ohms plus 1 over 100 ohms plus 47 ohms. This gives us a Thevenin resistance of 70 ohms. And to answer this question, this should also be the value of the load resistance in order for the maximum power transferred from the source to the load. Okay, so that's for part A. What about for part B? For part B, again, we do the same. So what we have here, we have a resistor R1, a resistor R2, and a voltage source which is equal to 3 volts. So to solve for the Thevenin voltage, we keep A and B open, so we don't factor in RL. Okay, and then what we have is a 3 volt source which are in series with R1 and R2. So we can actually redraw this circuit to be something like this. 3 volts. Here's your 3 volt circuit. This is your R2, which is equal to 270 ohms. And here we have our R1, which is 100 ohms. Now where's point A and B? Point A is here next to the positive terminal of 3 volts, and point B is here next to the intersection between R1 and R2. Okay, so this is point A, this is point B. Okay, perhaps this is now easier to see. If it isn't, we can still redraw the circuit to be like this, so that all the resistors are in the same line. So here's your 3 volts, this is your R2, which is 270 ohms, and this is your R1, which is 100 ohms. This is point B and this is point A. So that's point A right there and point B right here. Now this is probably easier to see, because now we easily recognize the voltage divider, but this time the voltage divider is seen across A and B. So in this case, the Thevenin resistance is derived from the voltage divider across R1. So R1 over R1 plus R2 times 3 volts. So this is equal to R1, which is 100 ohms, R1 100 ohms plus 270 ohms times 3 volts. So VTH is equal to 0.81 volts. Okay, next we solve for the Thevenin resistance. So going back to this circuit, we replace this by a short, okay, or if we go back to this circuit, we replace this by a short. Okay, and we now see that as viewed between A and B, R1 and R2 are parallel to each other. So that means that the Thevenin resistance is just 1 over R1 plus 1 over R2, which is equal to 1 over 100 ohms plus 1 over 270 ohms, so that Thevenin resistance is equal to 73 ohms. Now for part C, to solve for the Thevenin voltage, we ignore the load resistance across A and B. Okay, and this is actually already familiar to you because we've already solved this type of problem in the previous example. So the Thevenin voltage is easily solved using the voltage divider equation across R2. So the Thevenin voltage in that case is R2 over R1 plus R2 times 1.5 volts equal to 56 kilo ohms divided by 100 kilo ohm plus 56 kilo ohms times 1.5 volts. So the Thevenin voltage in that case is 0.54 volts. For the Thevenin resistance, we replace the source voltage with the short, which means that as seen across A and B, R1 and R2 are parallel to each other, so that the Thevenin resistance is nothing but 1 over R1 plus 1 over R2 is equal to 1 over 56 kilo ohms plus 1 over 100 kilo ohms, and the Thevenin resistance is equal to 36 kilo ohms.